Okay, so we in this video, again, we pick up where we left off on the process of reabsorption and secretion. Now, again, things to know. Here's a cell looking again at the proximal convoluted tubule. So the first part of the renal tubule. Here's our cells that make up the tubule. Here's where the filtrate is, interstitial fluids, and the peritubular capillaries we're trying to get stuff back into. And we said already that it's where most of the solutes are reabsorbed. So that on table 25.7, you see all the different things it can. And again, cumulatively, probably 70% of what you needed to return to the blood is coming back through these cells. So majority reabsorption. And there is some secretion as well, as we've already learned. So, you know, here again, it breaks down the percentages, but that's not the most important thing. Again, the most important concept is not to know specifically 67, 50, 100. It's just to know that the majority of solutes come back here, right? So this other consideration we talk about has to do with the formation of bicarbonate. Bicarbonate, we're going to learn in the next chapter, is a very, very important buffer. It's a weak base itself, so it can accept excess hydrogen ions. So again, plays an important role in acid-base balance. All right, and so what happens here in the proximal convoluted tubule is that there is a way for us to actually produce more bicarbonate. And you'll see that here's the key here, is as this bicarbonate is produced, it allows us to send the bicarbonate, reabsorbing, returning that, or it's new, so it's not really returning, it's making it and sending it to the blood to buffer. And we're also getting rid of hydrogen ions in the balance. We're tying up hydrogen so it's no longer free and able to change the pH. So just again for you to understand that what we're looking at here is a process by which the proximal convoluted tubule can make bicarbonate, and that bicarbonate can help us with acid-base balance. All right. So in the loops of Henle or nephronic loops, whichever term you want to talk about, so the proximal convoluted comes along, straightens out and moves down slightly into maybe the medulla, sometimes longer into the medulla. So what are we looking at here? So we're looking at the very tip of the loops. I said again, most don't go very far into the medulla, but sometimes we have these very long loops. The loops are specialized for sodium and water. Because again, we've done the majority of the things we needed. 100% of the glucose, amino acids, vitamins, and such have come back. So we're really focusing on some of the important solutes and, of course, more water. All right. So I say here that the transport is osmosis in the descending limb, and active transport in the ascending. So water's moved. So how water moves by osmosis because it moves towards the higher solutes. So it turns out that, and we don't see this specifically in this cartoon, that out here in the interstitial fluids surrounding these cells that make up the tubule is a whole lot of extra solutes. And that's what we're looking at right here. We're looking at the interstitial fluid osmolality. So the further down this loop goes, the higher this number becomes, and it maxes out about 1200 milliosmoles. Okay. Why is this important? Because this increase in concentration, because that's what the osmolarity is, or osmolality is here, is going to help move the waters, and we want to recover as much water as we need, all right? Because this is a place where decisions again are made. So water is moving out of this descending limb, as the arrows show you, and is being pulled out by these solutes in the interstitial, all right? Well, some of the solutes in the interstitial actually come from the ascending limb, because in the ascending limb, water does not move. These cells are impermeable. I mean, they won't allow water to move to the water molecule, while they actively push and pump sodium, and chloride follows it, into the interstitial. So this is part of what we call the countercurrent as well. And then it shows you here also in this cartoon that urea gets moved back and forth. It's being secreted at this point because it's out here and it's moving into. So urea is actually recycled and also assists with this concentration. But the take-home message for you guys again is that descending limb, water moves out and it moves by osmosis. It is pulled out by these high concentration solutes, and this is a very unique situation in the body. Typically, everywhere else in the body, 300 milliosmoles is a max, and that is an isotonic. This is becoming far more hypertonic. And this is showing you, rightfully so, that as the water leaves, of course, the solutes are staying in here, and urea is being pumped back in here. So we don't have a lot of solutes left, so urea helps to maintain this, and we get this greater and greater and greater concentration as well in here. All right? And then this high concentration, right, so we become hypertonic here. And as we move up the ascending limb back towards the distal convoluted tubule, we're going to lose those concentrations because, again, sodium's going to be pushed. And that sodium loss, without water following it, means that the filtrate actually becomes hypotonic. All right, so again, this just walks through descending limb of the loop. We have recovered a lot of solutes in water from the proximal convoluted, but we still have more. So osmosis occurs. These are simple squamous cells, and they have these permanent water channels. Like most of your cells in your body have these permanent water channels we call aquaporins. All right? So I say 15% of water can be reabsorbed here, right? So additionally, we left quite a bit, right? When we go back here, just pardon me for a second. We didn't talk about the water on this, okay. So 15% more of the water, because we haven't recovered all the water by the time we get done with the proximal convoluted tubule, can be reabsorbed because of the increase, right? This thing right here, increase in interstitial osmolarity and osmolality. All right? The ascending limb of the loop is a bunch of active transporters, right? Because the concentration of sodium is kind of low in here right now. We've really, and we have high concentration out here. So we have a simple, right, cuboidal cells, so thicker cells. That's why you see a thin wall and a thicker wall. We have these simple cuboidal cells again, no water channels. So this is completely impermeable. We cannot, water won't, and that's why we see this here. So sodium is reabsorbed, chloride follows, and this contributes. So these solutes help maintain this high concentration here in the interstitial. Water stays in the tubules, and the filtrate becomes hypotonic. All right, we call this the countercurrent multiplier. So, and this consists of, again, because the structure of the loops are very, very close to each other, and they're doing the opposite things. The vasorecta, this feature of the blood vessels, and specific blood vessels are, recta again means straight, so straight vessels are found here. So countercurrent, we call it that because the loops are next to each other and the filtrate is going in opposite directions. One limb going down, one coming up. Multiplier, it's because the action of these solute pumps that increase sodium will increase sodium and urea concentrations in the medulla. So in that interstitial, in the medulla, those medullary pyramids are very high concentrations of salts, all right, because urea as well is considered a salt. So how do we get this hyperosmotic interstitial? Well, again, as I said previously, the ascending limb, the sodium pumps, move it from the tubule to the interstitial. So we're constantly, right, resupplying, right, dumping more and more sodium into the interstitial. The collecting ducts have urea pumps that do the same. So urea keeps leaving. That's why we talk about urea recycling in the kidneys. So collecting ducts also have urea pumps, and that keeps dumping urea and sodium into the interstitial fluids, which maintains an exceptionally high or hypertonic solution in the kidneys. And again, the reason ultimately for this is that water. This will allow us to recover as much water as we possibly can, and generally into the vasorecta. All right? So here again, reabsorption, secretion, the distal convoluted. So we're back to our cartoon again to give you the big picture. And I'm saying, okay, by the time, so here's our water leaving, here's our solutes leaving here. All right, urea being recycled, okay, secreted and recycled. So here, by the time we get about here, we have 80% of the filtrate is back, right? So the solutes, the water, cumulatively 80% of it is back in the blood and back in the body, so reabsorbed. But we have still some that's going to come back so that we don't lose very much as urine, or we vary the amount we lose as urine according to our needs. But here again, we still have some more to come back. Most of it, as you see here, is sodiums, chlorides, bicarbonates, and water. So here in the distal convoluted tubule, we reabsorb sodium, chloride, calcium, and water. And these would vary. Again, if you had an excess of calcium already in the body, you wouldn't here. So these would be controlled, yes, by hormones. And that's what I say here. this reabsorption is variable, and it's due to aldosterone for sodiums, right? Reabsorb sodium, secrete potassium, and parathyroid hormones. And remember again, the chlorides just pretty much follow the sodium because negative follows positive. All right, so the collecting ducts and water recovery. So here again, we're looking at the cells in the collecting ducts. All right, and here's the filtrate, and here's, right, the peritubular capillaries still surrounding this. All right, so here they're showing you these little, in red, magenta, whatever color you want to call this, are these water channels. So the water channels only show up when we actually have antidiuretic hormone. So bear that in mind. But when they are there, then water, a maximum amount of water, will move from the filtrate, right, luminal collecting tubule, still got the filtrate, through the cells and back to the peritubular capillaries. Okay? So I say here, plenty of pumps and channels in these cells, right, because that's what they are, with two types of cells. So when we look at this, there'd be several, you know, they're just showing you a generic cartoon, but two types of cells dominate here. There are the cells called the principal cells, which help us recover or lose sodium and potassium. All right, so we still have an ability, and these are generally also sensitive to aldosterone, just like the distal convolute tubules were. So when aldosterone's around, the principal cells will help us reabsorb more sodium and secrete potassium. And this, of course, affects blood pressure because the water will go with the sodium. It doesn't go with the potassium. Right, so so volume changes because of the water, and so does pressure. Right, intercalated cells, right, they will secrete or absorb hydrogen and bicarbonate. So they're going to be very important in maintaining acid-base balance. So this is another type of cell found here, and you should just know what each cell is responsible for. All right, this is where we can restore concentrations of bodily fluids. Right, this is really the final, right. How much more water do we bring back? If you've been drinking a lot, we don't, right? So without these water channels, if we got rid of all these, water would stay in the filtrate and it just become urine, right? When we do not have enough water in the body, we're low on our levels, then antidiuretic hormone is made, right? And then water channels are put in place and more water can come back. And when more is returning, that means there's less here in the filtrate, so less water in the urine. Urine volume drops, and it becomes more concentrated. All right? So I say here, water balance is required to maintain blood concentration. Yeah, plasma has a certain osmolarity, how much stuff in how much water, because plasma is a liquid, and to keep liquid liquid, you got to have so much fluid, or, water, basically for us. So I said, need to keep all your solutions constant, isotonic, and what happens when you become dehydrated or consume lots of water? Well, here's our scenarios. If you're dehydrated, right, plasma osmolarity increases. That's a fancy word for saying you become more concentrated because you've lost the water, the solvent. So ADH in this circumstance will target principal cells to make, actually this should be intercalated cells to make water channels, and water is reabsorbed. So less urine formed, all right? If you have lots of water, all right, plasma osmolarity decreases, so your plasma is dilute. No ADH is made by the hypothalamus, and so no water channels or aquaporins are put into the ducts, and more urine is formed, right? And it's generally less concentrated. All right, so we'll come back to this idea of regulating renal blood flow on the next video. And again, mull these over, watch them again and again, and come with any questions you have.